The first talk is going to be given by Markus Greiner, and he will tell us all about something. Looking forward to it, Markus. Sorry, I lost the title, but you'll tell us.
Yeah, that's right. Sorry, I took away the title screen. Hello, everyone. So sorry I can't be there in person. I picked up a significant post-COVID condition after my COVID half a year ago, so I need to yeah, focus some of that. But I'm really glad that I can join via Zoom and that you guys allowed me to yeah, to do today's presentation on Zoom, and looking forward. Let me share this. Yeah. And so, yeah, so what I will be talking about is how we can really now bring quantum simulation to the next level in multiple ways. As you know, the Cold Atom platform is kind of the original quantum simulation platform, and it's going strong because there are some really nice advantages. So one thing is that we can create really large, very coherent many-body quantum systems in a very controlled fashion, right? We can also natively implement fermionic degrees of freedom, which of course is super helpful since fermionic systems, as you know, are particularly computationally complex to understand. And then, importantly, in these cold atom quantum simulations, we have quantum gas microscopy, where we can really manipulate and probe the system on a single particle level. So here's like a picture that I'm showing, I guess, since 15 years now, where you can see every single atom in a projective measurement. And so before, for example, you take this picture, every atom is quantum mechanically delocalized everywhere. And as they start to scatter the first photons, the quantum state collapses and you find a particular realization. And that, of course, gives you a lot of, like you stop time essentially and do a full measurement, a projective measurement of your quantum system. That's, of course, what in a real condensed matter system you can only dream about. Anyway, the great thing is that we very purely, very cleanly realize the Hubbard model. We can have a system where atoms only tunnel between neighboring sites to a very good precision, and if you have multiple particles on a site, there is pure on-site interaction. So two particles just raise the energy by U, right? As you know, so in 2002 already, we were able to do this with bosons. But as you'll see in my talks, of course, with fermions, we are pushing more and more in this direction. But what I want to talk about today is really well, while it's great that we can very cleanly realize this kind of simple, paradigmatic, plain vanilla Hubbard model in 1D or on a square lattice, we can actually now also start to really add additional terms, additional components in clean ways. And what I will be talking about today is doing this via artificial gauge fields. Doing this via Floquet techniques to create artificial gauge fields, for example, to create beyond on-site interaction, namely a fully programmable dipole-dipole interaction between particles, and create different geometries to create frustration, to create multi-band systems. Yeah. And yeah, let's jump right in. So with Floquet physics, you can kind of shake the system, and if you do it carefully, then you can really fairly arbitrarily program additional terms in your Hamiltonian. For example, a magnetic field, meaning the particles move as if they were charged particles in a magnetic field. And what we were able to observe and published in 2023 is that we could then create a two-particle fractional quantum Hall state, very similar to a Loveland state. So you can read up on this in this paper. More recently, we used the Floquet physics to create anionic physics. So here's the team of amazing graduate students doing that. The idea is that you can generalize, or so normally what's very much linked to anyons is that if you exchange two particles, you don't just get a 0 or pi phase shift, you get some other phase. But that, of course, implies that it now matters which way around the particles pass each other. But interestingly, you can extend this to one-dimensional systems in this kind of Fock space, essentially, and then you can have anyons in 1D. I don't have time to go into details here, but what we did experimentally is that we started with two particles where we gave, via Floquet physics, we gave the system the Hamiltonian of these 1D anyons. And then we can just see how these particles move under this Floquet dynamics. On the left is experiment, on the right is theory. So if we tune, we can arbitrarily tune this kind of phase. If we exchange them here, we have bosonic statistics, and we see that indeed a quantum walk or the correlation function, right? If you find one particle here, where do you find the other one? Looks exactly like you would expect. And for pseudo-fermions here, it also looks exactly what you calculate. But in between, you have this anionic statistics with the with interesting features. So this is a new kind of way. We also did some follow-up research where we really saw pairing between these particles and things like that. So if you're interested, look at that archive paper. Good. That's all I wanted to say about Floquet. What we can, right, let's jump into engineering interaction beyond simple on-site interaction. Here's the team of our new erbium experiment. The current grad students are Lin Su, Alec Douglas, and Mihao, and Augie is postdoc who has moved on now. And we started this experiment in collaboration with Francesca Ferlaino. The idea here is that we have tunneling and interaction, just like what I showed you earlier in the plain vanilla model, but now we also want a longer range term in our interaction, right? And a nice way to do that is if you use dipolar interaction. Now, what dipoles are there? So we are using magnetic dipoles. These erbium atoms are fairly magnetic. They have 7 e Bohr. But the problem is that this magnetic interaction is quite weak. It's only, we can actually boost it to 30 Hertz by creating a short spacing lattice. Right, but the question remained, can we then bring it into a regime where this interaction will then be dominant? There are other approaches, right, like optical cavities, Rydberg atoms, polar molecules, but so far these other platforms have not really gotten into the regime where you can really do strongly correlated physics at low entropies. And it's particularly interesting to study these models, of course, because these kind of like longer range interactions play an important role, for example, in moire materials or excitonic materials. So there's a very nice connection between condensed matter physics and the kind of quantum simulations we can do. So, as I said, we need short lattice spacing, and that created some challenges with microscopy. So we invented a new kind of microscopy. We first have this very tight spacing lattice, and then we increase that spacing by kind of moving laser beams around. And then we just do flash photography. We illuminate the sample of only a few microseconds with resonant light, and before the atoms can fly away, we collect enough photons.
For the one that we're looking at right now?
Yeah, the one.
This will pair with their conservation of energy.
I think someone is unmuted. Yeah, thank you. So we can take the snapshot and scatter photons, and they and we can get a perfect projective measurement. So the dipolar interaction we can actually tune by changing our magnetic field, right? And so then we can really kind of program, tune how much attraction, how much repulsion do the particles see in different lattice sites, depending on how you orient these dipoles. And if you do this, and if you work at half filling, right, then you get in the phase diagram kind of between the empty system and the n=1 mod insulator, where you normally just have a superfluid state. Around this half filling state, you get a whole zoom of whole zoo of quantum solids there, where the long range interaction is where the long range interaction gives rise to a very interesting, strongly correlated physics. So what do you expect here? So if you have the dipoles perpendicular to the 2D plane, then you get repulsion in all directions, right? And at half filling, if you have repulsion on a square lattice, what do you expect? Well, the atoms want to maximize their distance, and that, of course, they do in a checkerboard pattern. And so if you go into this regime, we were actually able to have the system do that. And here's a snapshot where you see that the atoms have arranged in a square pattern because they repel each other and want to maximize their distance. So this is a dipolar quantum solid. Of course, this kind of state at the endpoint is fairly classical, right? You just have one particle, no particle, one particle, no particle, similar to like a mod insulator or so. But of course, keep in mind, we are coming from a superfluid state here. We're coming from a state where every particle is everywhere, and then we do a quantum phase transition into such a checkerboard solid. We can also orient the dipoles in different ways, right? If we tilt the dipole into the plane, the atoms attract in one direction but repel in the other direction. And so you see these kind of stripes form where the atoms attract and repel. But of course, we have a whole lot of degrees of freedom. We can create interesting stripe states. And in the paper, we also discuss interesting non-equilibrium physics, where we, depending on how much time you give the system, you get very different periods here, depending on when the system loses adiabaticity. What's also interesting is that we started looking into, sorry, let me show this first here. You can, of course, characterize this via density correlators extracted from these pictures that we take. Or if you take the Fourier transform of that, you see the structure factor. So yeah, you can explore these dipolar quantum solids. And we also started to look into how we can go from one solid to another. They're interesting. There are also first order phase transitions present. And so there are a lot of interesting things to study. What we do right now is that we extend the system away from half filling. If you work around a unity filling, for example, then you get into interesting regimes where you expect SPT phases, topological phases. And so, for example, we've recently started going into a regime where you expect Haldane phases and so on. Yeah, it's a bit early for complete results there, but there are lots of possibilities that we can now start to explore having these dipolar interactions. Good, so that's dipole-dipole interaction. Let me come to the third topic, where we work with fermionic particles. But then, instead of just using a simple square lattice, we can really now explore different geometries, and it turns out that adds a lot to the system. Here's the team on the fermions. So here are grad students and postdoc. So the senior postdoc who led a lot of the work here is Martin Lebras, and the senior grad student are Muxing, Lev, and Erin, and Muxing, Anand, Lev, and Yuchi and Alex are new students. And we have a lot of great theory collaborators that we recently interacted with. Some of them are on the workshop. So Fermi Hubbard is really interesting because, in contrast to Bose-Hubbard, sorry. In contrast to Bose-Hubbard, the system becomes much, much more complex. You still have just simple nearest neighbor tunneling and on-site interaction, but then it turns out that if you have two spin states present, and if you're at low enough temperature, then you get into a regime where the spins also order. And this is because of super exchange, like some higher order process that favors opposite spins on neighboring lattice sites. Right, and that gives rise, for example, to an antiferromagnetic state that we have demonstrated a few years ago. Importantly, this model is famously linked to, is believed to be a minimal model for a lot of very exciting condensed matter physics. For example, things like high temperature superconductivity or so. You may have to add one term or another, but this is really a big playground, and it's extremely difficult to compute because of the fermionic sign problem. So this is a really great opportunity for quantum simulation to really benchmark theories, but also really try and discover new states of matter and so on. And so this progress is really accelerating recently a lot in our group. So the square lattice that you normally use things are very symmetric. For example, hole and particle doping have the same effect, and so this is really because of some symmetry that come from the Fermi surface nesting, and the right, but and as I said, yeah, away from half filling, you expect very rich phase diagrams with a pseudo gap physics, and down here superconducting D wave or stripes, charge density waves, and so on and so on. So, sorry, I need to see my slide. So how can new forms of magnetic order emerge away from a square lattice where you just have antiferromagnetism? Well, the first thing we started to explore is we implemented a new optical lattice potential that we can program in many different ways. One thing we can do is we can create triangular lattices. And if you have a triangular lattice, you get a strong spin frustration. Right? If neighboring spins wants to be opposite, well, the first two can be in opposite spin states and form a singlet, for example, but the third one doesn't know quite what to do, so you get spin frustration, right? And the other thing we can do is to do multi-band models, as I will show you. Let's focus on triangular lattice first. We can actually tune continuously from a square lattice to a triangular lattice by turning on this diagonal bond in a controlled fashion all the way to the point where the tunneling strength is the same and you get a pure triangular lattice. When we did this, we could nicely observe how you go for the square lattice from this kind of nice Neal order antiferromagnet. As we turn on this tunneling, we go into this regime where the neighboring atoms still tend to be anti-aligned, but of course the long-range order goes away. It's kind of what we saw is compatible with like 120, like towards 120 degree order, what you would classically expect. And yeah, but of course this gives rise to very interesting quantum physics around this point. To our surprise, what we actually observed as we started doping this system is, well, as you know, for square lattice, it doesn't matter. Do you dope holes or particles? It looks exactly the same, and that's what we also found experimentally. But on a triangular lattice, you find if you do hole doping here, then the antiferromagnetic correlations persist even more than on a square lattice. But on the particle doped side, there the negative tunneling of the particles really wants to suppress the antiferromagnet, but to our surprise, it actually went all the way into a ferromagnetic regime where nearest neighbor correlations become ferromagnetic if you dope the system strongly. So this kind of motivated us to look more into what the nature of this ferromagnetism is. And so, of course, one thing that is known to exist, or that had been proposed, is Nagaoka ferromagnetism. Of course, here this is fairly strong doping, so we decided to look more in the weak doping limit and see if we can explore Nagaoka ferromagnetism. So what is the idea here, right? In fact, Hubbard, actually, one reason for him to write down his model was actually to see if it could explain ferromagnetism. It turns out, because of the super exchange, it really always wants antiferromagnetism. But Nagaoka proposed only briefly after that if you turn your direction all the way to infinity, thereby essentially reducing your antiferromagnetism, reducing your super exchange to zero, then something really interesting happens. So for infinite U, a single particle above half filling, or similarly also a hole, would actually lead to a ground state that is a long-range ferromagnet. So how can that be? Why would the magnet care about dopants in this drastic way? Well, it turns out if you have a dopant, it wants to minimize its kinetic energy by delocalizing. But a dopant on a magnetic background, which has some structure, cannot easily do that. If a dopant takes one path or takes another path here, right, then the which path information is essentially encoded in the spin state. Depending on what path the dopant takes, the underlying spin is changing. And this is actually exactly like in a number puzzle here. Like imagine a hole moving here, right? And if you look at the numbers, you can identify which path the hole took, essentially. And that means different paths don't interfere. And that means a particle cannot delocalize and thereby minimize its kinetic energy. But if we have a uniform spin background, then it can delocalize, actually, because there's no which path information stored now. And so what we found experimentally is, indeed, if we dope the system weakly, and then we do a measurement where conditioned on where we find a hole or a doublon, a condition on where we find a doublon, we look at the magnetic environment around it, then we found that, so if we find a doublon at this location, the bonds around it, they tend to be ferromagnetic, right? So this is how much more ferromagnetic they are than average. And so that really means that kind of if you have a doublon here, it wants to delocalize in this region, and it can only do that if it convinces those spins here to align as well as possible. So that's exactly the idea of Nagaoka ferromagnetism, which we have been able to observe here. This is, of course, it's a curious kind of observation, but interestingly, as we know, in twisted bilayer systems, they recently also found some ferromagnetism, which is also expected or which is believed to link to a similar kinetic magnetism here. Good. So this is Nagaoka magnetism, but let's look at a different situation now. Can we program more complicated lattice structures to realize multi-band models? And so one interesting multi-band model is this Lieb lattice, which was originally motivated by the structure of cuprate materials, where you have different sub-lattices that essentially form a structure like this. But in general, right, a lot of interesting condensed matter materials just have multi-bands and have interesting, which leads to interesting band structures. And in this case, for the Lieb lattice, you have these p sites, which each have 2 bonds, and then you have the d sites, half as many of them, and each d site has 4 bonds. And it turns out if you do the band structure calculation, it turns out that this gives rise to a flat band. Let me show you why. Because you can see that the p sides here, right? The wave function for particle localized on the p sides has to change sign here, plus minus, and that means the tunneling amplitudes here cancel, and so that gives rise to this flat band. So this flat band here are the p sides, and the d sides are these non-flat bands. So Lieb proposed that for this kind of like flat band and for this situation, arbitrarily small interaction energy gives rise to ferromagnetism, but also over longer distances here you get antiferromagnetic order because these neighboring sites are opposite, and that's called ferrimagnetism. And so this is what we wanted to explore in this work. We realized these lattice structures actually by using our microscope in reverse to project potentials. So we essentially lift certain lattice sites a little bit in energy, and that takes them out of the picture. And so that way we can realize the Lieb lattice structure here in the center, as you see it on the picture. But this Lieb lattice structure is then coupled to a square lattice reservoir around it. And that's nice because now we can set a chemical potential essentially for, well, if we have equal spin mixture, just a general chemical potential, or if we have a spin imbalance, we can separately have a chemical potential for the up and down spins. And there's also thermal coupling, of course. And so the first thing we could nicely do is probe these flat bands, because this is Harvard's bosons. You can't just there's a nice experiment by Takahashi and also the Bloch group with bosons, but there it's hard to really probe this. But with fermions, we can just vary the chemical potential and see how the bands fill up. And what we found is if you look at the D sides here, you can see at first the D band fills, then it's flat, and then the D band fills again as we come up here. First this one fills, and then the P band corresponding to the flat band fills fairly quickly here. And then after that, the second D band fills. If we take the derivative of this, the local density of state looks like this. So again, red are the P sides and blue the D sides. So we can nicely see that kind of flat band emerge. But what happens now if we crank up the interaction? And as Lieb predicted, is that at that point we don't have a density modulation anymore, and the right, and we can look at the spin correlation in this case, and see how the spin correlations emerge here with the bond length as shown here as we go into this Lieb lattice system. But how about ferrimagnetism? So if you have ferrimagnetism, you would now expect that that if you create a spin imbalance, that the sublattices are differently populated with a spin up and spin down, because as Lieb predicted, you would have a net magnetic momentum. So for no or just a very weak spin imbalance, we see no significant pattern. But if we now increase the spin imbalance, then you can see how the two sublattices, the population with up and down spins changes a lot here, right? So the P and D sublattices are populated with one or the other spin state significantly more. We can measure how much that is, right? So this is the comparison in the square lattice as we introduce the spin imbalance, which is equal to applying a Zeeman field. Nothing happens, but the P sides in the Lieb lattice, they grow very quickly in density with that Zeeman field, whereas the D sides, they actually reduce they actually populate with the opposite spin state, right? which really nicely shows this paramagnetism here as we introduce the Zeeman field. So this is interesting non-monotonic behavior here, which is really the hallmark of that. This whole thing, as Lieb predicted, is robust to interactions. So in the small interaction limit, right, here you can understand it in terms of band physics, and the flat band gets polarized. But here in the strongly correlated one, then you need this kind of antiferromagnetic picture. But the effect is actually strongest in between, as we were able to measure here. Of course, this is very robust, so we can dope away from half filling. And one curious thing is we measured the local compressibility, and interestingly, what you actually find is some kind of period doubling in that kind of structure. So here is, as a function of chemical potential shift, the P and the D sides, the density of states, changes like this. But then for very strong interaction, you see that that same structure appears twice here. And so one way to maybe understand that is that you're in some kind of hardcore, both the limit, hardcore fermion limit here, such that this part here maps onto this. Well, anyway. Good. So let me summarize this. We realized this multi-band Fermi-Hubbard model with a flat band in the middle, and we're nicely able to show this and see the magnetic state. And this ferromagnetic state is, as predicted, very robust to interactions. So what we really kind of want to do now, and just 1 minute, Caden Haffer. What we really want to do now is, or what would be super exciting is if you can further lower the temperatures, right? Here's a nice review paper by Annabelle. And what you see are the temperatures where different experiments are kind of at the lowest temperature so far, where what we reported here. But of course, you want to be a bit lower to really get into these interesting states of the Fermi-Hubbard model, where there will be a lot of things to explore. So how can that be done? There's a famous proposal where the idea is you start with a band insulator, which is a gapped state. And indeed, we can experimentally create very, very pure band insulators with amazingly low entropy. But of course, the band insulator is boring. You then have to turn it into an interesting state in some adiabatic way. And the idea is to turn each side into a double well. So a local singlet turns onto a singlet in a double well. And if you then make that tunneling equal, then there should be a good path to interesting many-body physics. And I don't have time to go into this, but let me show you. We have recently used our new lattice to start doing this, and all I want to say, it looks really, really, really promising. So this is, for example, at half filling here, where we get a really strong antiferromagnetic correlation, close to what you expect for extremely low temperature, and the temperatures are, it seemed to be possible to reduce the temperatures by a factor of a few. It still remains to be seen how much, but it looks extremely promising right now, and we can't wait to really explore the low temperature phases of the Fermi-Hubbard model. Okay, with that, I would like to thank the whole team and collaborators, and thank you very much for your attention.
Great. Thank you, Markus, for the fantastic talk. We'll take time for a couple questions.
Thank you. Yeah, thank you very much for this nice talk. The Nagaosa cloud or bubble is supposed to change its size with you with a simple power law. Could you check that? And can you comment on the difference between holes and particles? I guess for one, the kinetic energy is fluctuating, and for the other, it's not. But can I say more than that?
Sorry, Caden, could you briefly repeat the question closer to the laptop? I think this is just.
You just want to come ask it up here.
All right. Okay. So Can you comment on the size of the Nagausa cloud? Have you checked how it changes with U? And can you comment on the difference between hole and particle doping?
Yeah. So so the difference of hole and particle doping is, in one case, it becomes ferromagnetic, and in the other case, it becomes anti-ferromagnetic. So that indeed we can see nicely, and this is because of the sign change. If you have a in the tunneling in the effective model, if you have a doublon or a hole, and so yes, we can see that. We don't want to make too strong claims about the size of the Nagaoka bubble. The reason is that, let's say, the way we analyze it, the bubble is as big, roughly as, or it becomes big enough that it's comparable to the distance to the next doublon, and at that point, one has it's kind of like you can't tell anymore that this bubble is then uniquely from that one dopant. So we decided not to make really claims on the size of that bubble. Of course, we have some data for like really small bubbles in some regime, but yeah. Yeah.
Someone has a really quick question. We can take it now. Anybody wanna- Okay, I think we should keep moving to keep things on time. Thanks a lot, Markus. For
Sounds
the
good.
beautiful
Thanks so
talk.
much.